Hello, and welcome to our penultimate installment of GMAT and GRE Prep Club's GRE Preparation Complete Series. It's almost over, but it'll never truly be over because things on YouTube live forever. Next week will be our very last episode in this series, and it's going to be about how to break through your quant scoring plateau. Not that you will need it, you're doing great, but just in case. Today, though, today's a different story. If you're here, maybe you know today's about quantitative comparisons, a pretty major part of quant. Not the majority of quant, but major. Always at the beginning of the quant section, kind of sets the tone for the entire section, right? Like if you spend too long in quantitative comparison, you're playing from the back heel for the rest of the section, and that usually leads to bad outcomes. If you get quantitative comparison questions wrong, which a lot of people do, it's often going to go by like totally unnoticed. Quantitative comparisons are ninjas. They're the silent killers. In that, it's very easy to get them wrong and not know that you're getting them wrong. And that's down to the fact that the answer choices don't really do you any favors. All right. Whatever answer you convince yourself of in quantitative comparison, it's there. That answer choice is there, right? So you can talk yourself into anything. And the question's going to be, yeah, but how do you talk yourself out of picking the wrong answer? Guys, if you want to see the rest of the videos in this series, links are below the video. Check them out. But if you are here, lock in because we're doing this now. As always, for anybody who's attended any of my previous sessions, there are going to be problems. I'm going to give you time to do them. You guys can play along. You can show who's going to be the very best, like no one ever was. All right. Be the Ash Ketchum of the GRE. Here we go. So, what are we doing? We're going to talk, of course, about quantitative comparison generally. And if you've been to some of these other presentations, you've seen quantitative comparison questions. I know I didn't shy away from putting them in the earlier presentations, so you kind of know the score. But I want this to serve as a kind of start to finish presentation of what quantitative comparison is, just in case you're totally new here. Welcome. You've missed a great series. Links below the video. And so we're all on the same page going forward, all right? But hopefully I can shed some more light on this particularly pernicious question type from the GRE Quant sections. All right, we're going to start by figuring out what these problems are and generally speaking how we can approach them. And then we're going to take that and apply it to questions that come from each of the 4 topic areas tested on the GRE. So you see there, arithmetic, algebra, geometry, and data analysis. Roughly in that order. It's gonna be great. Put your thinking caps on. Let's go. Big picture of the GRE. Remember, you're going to get 2 quant sections, 2 verbal sections. And again, the quantitative comparison questions will always come at the beginning of the quant section. So you're going to have probably about 3, 4 in your first quant section. In your second quant section, it'll be more like 4 or 5. So a good like quarter to a third of your quant sections will be this. All right. And one of the hallmarks of quantitative comparison is that there are multiple ways to solve these problems. So one thing you're looking for is efficiency. Let's talk about that. Talk about these problems. Starting with this one, which may be a bit familiar to those of you who have been with us before. Now, we're not going to properly do this problem. Let me just talk to you about it. The most basic quantitative comparison setup has just 2 things, really. Quantity A, seen here on the left, and always on the left, and quantity B, seen here on the right. Now, can there be more to a quantitative comparison question? You bet there can, and we're going to see that in a moment. But at the very most basic level, you're going to have a quantity A, a quantity B, and you're going to have these 4 answer choices. These answer choices never change, and as I implied before, they kind of account for everything that can happen in quantitative comparison, all right? So let's start there. Answer choice A is always going to say quantity A is greater, right? You choose it if quantity A is unequivocally, always, in all circumstances, greater than quantity B. B, as you might expect, says the opposite in favor of B, right? You choose B if quantity B is unequivocally, any sort of doubts, in every possible case, or at least every allowable case, bigger than quantity A. You choose C if the two quantities are, beyond any shadow of a doubt, unequivocally equal to each other. And then there's D. D is the answer choice that makes quantitative comparison the worst. All right? Because D is saying the relationship cannot be determined from the information given. And what that practically means, as you're considering quantitative comparison, is you can get two different relationships between the quantities, right? So A, you choose if A is always bigger. B, you choose if B is always bigger. C, you choose if the two quantities are always undeniably equal. D is what you choose if it could go either way. If in some cases A is bigger and in some cases B is bigger, or in some cases B is bigger and in other cases the two quantities are equal. If you can show that the relationship between these two quantities is not certain, is not fixed in place, if you can show that two different relationships between these quantities are possible, that's when you pick D. All right. Now, there are going to be certain quantitative comparison problems for which D is just not really a possible answer. It's not a viable candidate. All right. And it's a good idea to just acknowledge that upfront in a problem. Are we playing toward D in this problem, or is this a different thing? You won't always know perfectly. Err on the side of caution. All right. If there are variables, if there are unknown values in either of the quantities or somewhere in the problem, D's on the table. But you have a problem that looks like this. And these are not super uncommon on the GRE. That is to say, if you have a problem in which quantity A is a bunch O numbers and quantity B is a bunch O numbers, or one number, as the case may be, D's not on the table, right? Because the values are known, right? The relationship between these two quantities is going to be fixed. Now, it may be that the problem is so complicated that you can't figure out what that value is, right? It's like they will definitely do that. For instance, in this one, if you don't know what negative exponents do, that's going to be a fairly tough one to figure out. You might find yourself guessing. But what you shouldn't be guessing in this problem is D, because even if you don't know what negative exponents do, you can at least be sure that they do something predictable. And so you're going to be able to, in a perfect world, get a number for quantity A. And in the end, you're just going to be comparing that number that quantity A yields to the number that quantity B yields, right? If A comes out bigger, you choose A. B comes out bigger, you choose B. And of course, if they come out equal, you cry. Because that can happen. Just kidding. You choose C. In this particular case, spoiler alert, again, this isn't one we're doing properly, they do come out equal. And just as a quick pointer to anybody who doesn't know what negative exponents do, 1, check out the exponents in quadratics lesson. It is a banger. And 2, they just take the base and flip it. They invert it. So this would be 5 to the 1 plus 5 squared plus 5 cubed. Which makes them really useful here because it means in getting rid of the negativity in the exponents, you also get rid of the fractions within the fraction. And so you're kind of cruising. From there on, it's all just calculation. Quick note, no exponent button on the calculator, right? And so with 5 to the 1, 5 squared, 5 to the 3rd, these are values you should have memorized anyway. But if they were bigger powers, you might have to pull something else off here, right? Again, for anybody who was just idly wondering, they do come out equal to each other. But no idea how. I just trust. I just believe. All right. We're talking still about the anatomy of quantitative comparison. So we know what the answer choices are. We know what the most basic look on quantitative comparison is. Number and quantity A, number and quantity B. Now, let's kick it up a notch, as the late, great Emeril Lagasse used to say. Just kidding, I don't think he's dead. Here's a case in which two things have changed. There are variables in the quantities, right? There are unknowns, which immediately means D's on the table. Now, that's not to say the answer is going to be D, but it is to say that you've got to consider D as a possibility here, whereas in the previous question, you really shouldn't, all right? The other new thing is you got this information top center here. Right? X, Y, Z is greater than 0. That is to say, X times Y times Z is greater than 0. That's what we'll usually call given information, right? It's a constraint you have to operate under throughout this problem. All right. So in this case, we're given some information up front. And it's not going to be the case that every problem in QC with variables in the two quantities will give you information about those variables. Sometimes it's just some variables versus some variables. All right. But you are given any information on the unknowns in the problem, if you're given any words up top, a story type thing, because there are word problems in quantitative comparison. If you're given something more algebraic looking like this, you have to bear it in mind as you go through the problem, right? It's going to be in some way meaningful or misleading. Who knows? Who knows? We shall see. Now, another thing that's going to play out in a lot of quantitative comparison problems, and it's kind of on display here. There are going to be a lot of cases in which a quantitative comparison problem on its surface looks like it's pretty clearly going to go one way. All right. And this is one of the major factors that contribute to quantitative comparison being such a ninja problem type, right? That they'll come on looking all innocent. This one might be a good example of that, right? We have the average of x, y, and z on the left. We have the average of 2x, 2y, and 2z on the right. On the surface, looks a bit like quantity B should win because it should be kind of double whatever quantity A is, right? Just on the surface, especially bearing in mind that x, y, z here is positive, right? So the right mentality to take in quantitative comparison, anytime you see them trying to go for what feels like an obvious answer, is no way, bro. Nah, bro. All right. They want you to pick B here. You should acknowledge up front in a question like this that B is a possibility. Like, yeah, it's very likely that you're going to find a case that makes quantity B bigger than quantity A. But that just means that you're going to want to try to play against quantity B as it goes. Now, how do you play this whole thing? So, I talked about approaches before, a little bit. We're going to talk about approaches. This is where it really begins. Right. This is a fairly algebraic problem. And one thing you can certainly do, if you're so inclined, because the word average is mentioned, use the average formula, right? So on quantity A, x plus y plus z over 3 is what that average would be. On quantity B, 2x plus 2y plus 2z. All over 3 again. And the inclination early on in quantitative comparison is, especially when you have variables, of course, pretty exclusively when you have variables, to just try to pick numbers for those variables, make up an x, y, and a z, right? That's something I'm going to call the numerical approach, or testing cases. All right, the numerical approach in quantitative comparison is usually testing cases, which is to say, you rarely want to pick just one set of numbers in quantitative comparison. You usually want to pick like 2 sets of numbers, unless you acknowledge up front something like in this problem. Okay, B's pretty clearly got an avenue to the win. Then you really, if you're testing a case, are just trying to test a case that maybe makes the 2 sides equal or gives A the win in some way, right? But testing cases is by and large the numerical approach. And the simplest way I can put things is this, you guys. You should basically never go straight to testing cases in quantitative comparison. There are going to be some times when you got no other options. It's the only path you see. In those cases, absolutely, by all means, go ahead. But you should at least be considering your alternative approaches before going to testing cases. What are those alternative approaches? Literally have no idea. I just got hired here. No, they're algebra and logic. All right, algebra and logic. And whether you use algebra or logic depends largely on how algebraic the problem is. They can both work really well. They can both do a lot of the same jobs. And they often work really well in conjunction with each other. A bit of algebra to clean it up, a bit of logic about whatever you've gotten as the result, right? Testing cases should be used after algebra and or logic has its say, right? When you're testing cases, you're trying to push for an answer of D. You're trying to show that you can get two different relationships. You don't usually want to test cases up front in a problem because consider this one. If you test cases right now, after having just kind of like translated those two quantities into expressions like this, what are you doing? You're picking a number for x, a number for y, a number of z, making sure, of course, that that given up top is observed, is respected, right? And then you're taking those three numbers and you're plugging them in to the left thing. And then you're taking them and plugging them into the right thing and doubling them and dividing by 3 and adding up and all these things, right? So there are actually like a few steps that go into every case you might want to test right now, right? And it can be hard to know which direction should I go from here, from where I just was, right? If you do algebra up front, or if you use logic up front, you can often either obviate the need to test cases at all, or if nothing else, get some insight into what kind of cases will really matter. You can also make it so that each case you test requires a bit less work. All right. Let me introduce here the algebraic approach. So what does it mean to do algebra in the quantities? To some degree, we've already done algebra in the quantities, right? It's like we've got our x plus y plus z over 3, our 2x plus 2y plus 2z over 3. But the real unlock for algebra in quantitative comparisons, get those answer choices out of the way. Who needs them? Real algebraic unlock is that you can do algebra to both sides, to both quantities. You can do algebra to these two sides as though they were two sides of an inequality, right? Because maybe quantity A is greater than quantity B. Maybe quantity B is greater than quantity A. Maybe they're equal. If you kind of pretend for the moment that there's an inequality sign there, that you just had these kind of two things, plus z over 3 as kind of a sidebar here is greater than 2x plus 2y plus 2z. And if you think about what kind of algebra you would typically do in a problem that looked like that, largely this is going to be algebra you can do in quantitative comparison. That is, you can do the same thing to both sides of a quantitative comparison within certain limits, all right? You can add or subtract anything you want to both sides. If you want to add an a to both sides right now, the variable a, totally can. Shouldn't. It's not going to help you, but you totally can. If you want to, maybe more productively, multiply both sides by something or divide both sides by something, you absolutely can as well. But that's where the constraint comes in. All right, so rules are you can add or subtract anything you want to both quantities, but you can only multiply or divide both quantities by positive values because of inequality rules, right? What happens when you multiply both sides of an inequality by a negative number? That sign flips. And you don't want that drama in quantitative comparison. You don't even want to be thinking it. More to the point, though, what you really, really don't want to do algebraically in quantitative comparison is multiply both sides by a variable, let's say, if you don't know that variable's sign, or by an expression, if you don't know that expression's sign, if you don't know for sure that that variable or that expression represents a positive number. Don't want to do it, all right? But in a case like this, when you've got like 3 on the bottom of both sides, 3 is a positive number. Totally, you're well within your rights to multiply both sides by 3. Again, presumably exactly as you'd want to do if you were in this situation down here, if it were just a normal inequalities problem and nothing to do with quantitative comparison at all. Right? And look, that makes both sides a little bit easier, right? You've got x plus y plus z now, and you don't have to worry about dividing by 3. That means that if you go to test cases from this juncture, you've got 2 fewer math steps to do. You don't need to divide the left side by 3 anymore. You don't need to divide the right side by 3 anymore. But we can do better, because we got like terms on both sides of this quantitative comparison still. And those like terms are joined by addition in all these cases. And you can always add or subtract anything you want, regardless of its sign, to both sides. So what if we just full on subtract x plus y plus z from both sides? What if we did? Who's going to stop us? Nobody. That's who. Now you might say, but dude, that just disappears everything from the left side, and you're not wrong. That's part of its charm. I don't know why the minus sign won't show up here, but trust me, I'm minusing this stuff. Come on, one more shot at the minus sign. Oh, it's kind of there. We'll just have to make do. It's gone now. What are you left with? 0 over here. What are you left with over here? X plus y plus z. Now there's still some uncertainty here, but what has this actually done for us? One thing, it means if we want to test cases for x, y, and z now, rather than have to plug values into 6 different spots, right? The x, the y, the z on the left, and the 2x, the 2y, the 2z on the right, rather than have to multiply 3 of those numbers by 2, we can just plug numbers into 3 spots, all on one side, x, y, z, just there. But perhaps the more subtle and more important thing that this shows us is this. Right now we're in a position in which quantity A is 0. Let's highlight this a little bit by making it blue. And quantity B is just x plus y plus z. That setup gives you a huge hint as to what you should really be thinking about with x, y, and z over there, right? Because what this problem boils down to is whether x plus y plus z is greater than 0. Another way of putting that, whether x plus y plus z is positive. And that, in turn, invites the question, could x plus y plus z be negative? And to answer that question, you come up here. And this is where maybe logic skills come into play a little bit, right? We know that x times y times z, those 3 numbers multiplied by each other, come out positive. Does that mean that each individually has to be positive? Or not so much? Remember, you guys, participate in the chat. It'll be fun. Stay one step ahead. Be heroes. In this case, no, not necessarily. X plus y plus z, or x, y, and z individually can all be positive, right? If they are, that rule is honored, as it must ever be. So if it's positive times positive times positive, check. That gives you a value bigger than 0. And if that's the case, quantity B wins, right? But this sneaky side case is that 2 of them could be negative. Not all 3 of them, right? Because you got 3 things there. But 2 of them, yes. If only 2 of them are negative and they multiply by each other, that's going to turn positive, right? If x and y are negative, x times y is positive. Multiply that by z when z is also positive, and you got a winner, right? And therein lies why this one turns out to be D. If x, y, and z are all positive, then B wins, right? But if x and y are negative and z is positive, you could at least see a situation in which side A wins, in which 0 comes out as the winner. All right. Pick specific numbers if you want to prove it to yourself. And I would say early on in your quantitative comparison career, you should pick numbers. You should pick the actual numbers and make sure. But you don't want to go into testing cases without some kind of algebraic clearing or some kind of like logical insight, if you can get them. All right. This is an example of us getting both. The algebraic clearing early on led to some conceptual, some logical insights. Like logically, this is about whether x plus y plus z is positive or not, right? And you could have started with that. You could have looked at this and said, well, yeah, but 2x, 2y, and 2z won't necessarily be bigger than x, y, and z if there are some negatives there. You never have to do the algebra here at all. The algebra, though, clears away a lot of noise that doesn't need to be there in problems. All right, it is a powerful tool in quantitative comparison, and it's one of the most underutilized in my experience. People don't love to do algebra and quantitative comparison because people don't love getting problems right. But you should. You should try to get these problems right, and I'd say an instrumental part of doing so is using algebra up front in quantitative comparison, right? So algebra and logic first, numbers second. All right, if you don't come up with anything algebraic you can do, or you don't have any logical insight to the problem, then go to numbers and try your best. All right, but every algebraic thing you do up front makes number testing more efficient because you'll have fewer and fewer places to have to plug those numbers into, and makes number testing more efficient because you're more likely to have a clear insight into what numbers will make a difference here, right? Remember, when it does come time to test cases, you're playing for D. You're trying to show maybe this side could come out bigger, maybe that side could come out bigger, or maybe this side could come out bigger, maybe they could be equal. Show two different relationships. You got D, and this one is absolutely going to be D. You can pick X and Y as like rather big negative numbers, -10 and -10. Pick Z as a small positive number like 2, and 0 is going to beat X plus Y plus Z pretty handily, right? And notice, a lot easier to see that X plus Y plus Z will lose at that point than even when we had it as average of and average of in the original iteration, all right? Algebra and logic make it easier to see what the problem really is, and it's how these things are designed, all right? So we're going to bear that in mind as we go forward through this whole adventure, all right? We now understand what QC problems are. We understand some of the approaches on QC problems. This is your first opportunity. This time I'm going to hang back 30 seconds, 45 seconds. If you're here right now, I don't know that anybody is. But if you're here right now, take a crack at this. Tell me in the chat window what you think the answer is. If you're watching this on YouTube, I like YouTube too. Pause it, try this problem, and then continue. All right. So far, nobody's got an answer in. Try if you can. You're watching this on YouTube. May have been 10 minutes since we last saw each other. Hey, how's the future? Hope it's grand. Have my doubts. This is one, first and foremost, it's full of numbers. You shouldn't pick D in this one, right? Because these are certain and established values, right? They're pinned down. There's no unknowns here, right? Now, again, GRE calculator doesn't have an exponents button, so it's not going to be particularly easy to calculate these numbers, but it's at least possible, right? You can just sit there and multiply 3 a bunch of times. Get to 3 to the 7th, write it down, go 2 more, get to 3 to the 9th, write it down, boom, 9 to the 4th, everything's going to be fine, all right? But usually you won't be required to use the calculator to get to exponential powers that big. All right, so it's a bit of a red flag, bit of a time waster, but you will get an answer. All right, what's the clever QC way of doing it? Great question. Great question. There's an opportunity here, right, between these two quantities. You can rewrite the 9 as 3's, and probably should. All the other terms here are 3's. 9 is made of 3's. You just rewrite the 9 as 3's. You could factor stuff out, which you often would in an exponent setup like this. Same bases, plus or minus between them. Factoring can be a great call. I'm not even saying it's a bad call here. It might be the best call. But I think in actuality, the best call here, you guys, as a first step, is recognizing both of these quantities have something in common. A minus 3 to the 9th, right? Logically, since it's on both sides and it's minus on both sides, it's kind of in the same position. Logically, that 3 to the 9th can't be affecting whether quantity A or quantity B is bigger, right? It's a wash. It's the same on both sides. That part of each quantity is a tie. Algebraically, you can disappear it by adding 3 to the 9th to both sides. And you absolutely should. Even if you're going to go on to use the calculator from there, you're going to save yourself a lot of time. All right, 3 to the 7th. And 9 to the 4th. not as much to calculate. But you're not going to. The thing to do here really is now to get some common ground between the two sides, because that's one of the things about quantitative comparison as well. Not only do you want to kind of exploit the common ground between the two sides to do some algebra, clear some stuff away, and make your life easier, but you want to always bear in mind that these are not necessarily calculation problems, right? They've got discrete quant for that. They've got data interpretation for that. They've got plenty of places to make you calculate values of things. These are comparison problems. And you only really need to go as far as is necessary to decide which side is bigger or if they're equal, right? You don't necessarily have to calculate everything out. In this case, if you're comfortable with exponents, you absolutely should play this as replace 9 with 3 squared, because that's what it is. Take that to the 4th power, and of course, the rule of exponents says this is going to be 3 to the 8th. Those two exponents are going to multiply by each other. And 3 to the 8th beats 3 to the 7th. Right? But if you're not super comfortable with exponents yet, absolutely use the calculator at that point. Even if you're going to use the calculator, if you're going to do anything numerical, doing algebra up front makes it easier. Right? And that means that as part of your kind of GRE journey, you want to get really good at algebra. It helps a lot in algebra problems, as you might expect, but it also helps a lot in quantitative comparison problems, helps a lot in geometry problems. Algebra is one of the pillars of a successful effort at the GRE, at least as far as quant is concerned. You don't need it in verbal to the same degree. All right. In QC, algebra is, again, major underutilized weapon. All right. You've got to use it. Brandish it against the GRE. All right. A bit of algebra was possible there. It was great. Now, have a look at this one. And again, I'm going to hang back for, 30-ish seconds or so. Maybe a minute. Whatever's clever. And give you guys a chance to work on this. Still waiting for our first answer from anybody attending this session live. And you guys, don't be strangers. It's so much more fun when you say things. Even if you're just like, I'm logging in from Abu Dhabi. Right? Say hello in the comments. All right, that has been about, I have no idea how many seconds. And it felt like an eternity. And even though this problem kind of looks like it requires a lot of calculation, that amount of time is actually enough time to get to an answer here fairly confidently, if you approach it in the ideal way, right? So QC problems are often going to tempt you to do more math than you really need to do. Building on what we said last time, right? These are comparison questions. These aren't like calculation questions. QC problems are going to tempt you to do more math than you need to do, right? And that is how they then take your time away. And that is how they then ruin the rest of the section. And so one of the key things about QC problems is there's generally going to be a faster way and a slower way. And when you're studying these problems, when you're reviewing them, make sure that you're pushing for the faster way. Keep cycling through. Okay, was there an algebra play? Was there a logic play? Was there a numerical play? Here, there's absolutely a numerical play. You can use the information up top. 66,000 citizens, average of $55,000, 73,000 citizens, average of $45,000 salary. And calculate the average salary of all the citizens of both towns. You'd need to get the total salary for the two towns, and then you'd need to divide it by the total number of citizens in the two towns. Bish, bash, bosh, you're good. Now, one complication to that in this problem is GRE calculator only has 8 digits to display. And 66,000 times 55,000 comes in at more than 8 digits. And so that complicates efforts a little bit to do the proper math here, right? You can make adjustments. Turns out even if you treat town X as 66 citizens and town Y as 73 citizens, you're going to come to the exact same answer. And so that's one workaround, and that's going to be useful to you, by the way, when using the GRE calculator for things like data interpretation. All right, sometimes you have to truncate the numbers and just live with it. But it's not the best way to go about this one. Because nowhere is this whole compare, don't calculate advice more salient than in quantitative comparison questions that look like this. By look like this, I mean they have a fairly complicated thing to figure out in quantity A, and they have a plain old number in quantity B. All right. The majority of the time you see a setup like this, not all the time, but the majority of the time you see a setup like this, what you want to be thinking is, what's the significance of that number in quantity B? Because sometimes they just pop a random number in there. Honestly, it happens. But more often, they've chosen that number specially, right? And you might have noticed it even as you were doing this problem. 50,000 is the halfway point. Halfway point between 45,000 and 55,000. That is to say, it's what you'd get if you averaged those two salaries, right? Town X's salary and town Y's salary. If the average were a balanced average. But this average isn't, right? Because town Y has more citizens. So if we think of the average as falling somewhere on this spectrum between town X's 55,000 and town Y's 45,000, boom. And if we think of 50,000 quantity B as the break-even point, the fact that town Y has more citizens means they're going to have more pull on the average, right? They're going to win this. You think of it as a tug of war. They're pulling harder with their 7,000 extra citizens, and the average is going to end up somewhere over here, somewhere to the left of the 50,000 mark. That makes B the winner. And that right there, you guys, is an example of a logical approach. I know we talked about it a little bit with x plus y plus z versus 2x plus 2y plus 2z. But this one you can do on pure logic. You wouldn't do it algebraically. There are no unknowns here to solve for or anything like that. But you wouldn't want to do it just by calculation really either, because you'll spend an unnecessary amount of time doing it that way. All right. So logical insights save you time. Algebraic insights save you time and make things more clear. All right. They are the way to go up front. And barring anything like that, like if you were looking at this and saying, I didn't know that was possible, I was never going to do that in a million years, then yeah, fall back to numbers, right? Like you wouldn't want to just not do this problem because it's like inconvenient to work with the numbers. Find a way to make the numbers somewhat convenient and just go for it. But spend on test day, when you finally get there, make sure you're spending the first at least like 20 seconds of a quantitative comparison problem thinking, I got any algebra, I got any logic I can use, right? Give them the right of first refusal before passing to numbers, before passing to heavy calculation. Okay. On we go. All right. Last of our kind of general approach to quantitative comparison series, and after this we're going into specific topics, though you might have noticed we've already touched on a few topics: data analysis, arithmetic, a bit of algebra-ish here. All right, as is my custom, I'm gonna hang back for 30 seconds or so, let y'all think about this. There's a prize for anybody who gives me the first right answer in this live session. Only no, there's not. That's a total lie. Good luck. All right, so about this problem. First, this one might well fall under a category of, I feel like they're trying to push me in one direction here. I feel like they're trying to get me to pick something up front, right? Because what do we have? We have a times b is not equal to 0, just meaning that neither of them individually is equal to 0, right? And usually that's what it is. They give you something and you've got to interpret that something in some way, even if it's fairly innocuous like this. Neither a nor b is 0. And a to the x power equals b to the x power. It feels like they're pushing a strong pick C agenda here, right? Like a and b could and probably should be equal to each other if a to some power is equal to b to the same power. Right? So you kind of know up front that C is a possibility. Right? And that means, practically speaking, you're limited to 2 answers now, right? Since looking at this, C is, again, fairly decidedly a possibility. Right? It looks like C. Looks like the 2 sides should be equal. What that really means for you practically is you can get rid of A and B as answers. You know that C is a possibility here, and so you've got a 50-50 shot at this point. Either, yeah, they're totally equal. It's everything is as it seems. No trickery here. Or there is some trickery, and so you're going to pick D. They don't always have to be equal. Right? I've seen a lot of people do this problem, and even when you suspect that C is a trap answer, it can be hard to actually come up with a case that gives you any other result, right? A case that makes quantity A bigger or quantity B bigger. Enter Zone F. Enter Zone F. You guys, I've kind of like come down hard on testing cases. I've kind of made it seem like an unappetizing option. I realize that, but the fact is, to prove that D is the answer, you often will have to test cases, and D will be the answer often enough that you want to be good at testing cases. And we talked earlier about how algebra and logic upfront will unlock the cases you should be testing later on and make it a lot more efficient to test cases. But the other thing that makes your case testing successful, Zone F. All right, Zone F is basically an acronym to remind you of the weird cases to test. Z for 0, O for 1, N for negatives, E for extremes, and F for fractions. And by way of quick example, when we talk about extremes, it's kind of like if they tell you that x is less than 10, extremes would be something like, well, it could be 9.9, unless there's an integer constraint. Or it could be like negative 10. It could go extremely close to that border of 10. It could be extremely far away from that border of 10. Right? Fractions, we're typically talking about fractions between 0 and 1 or between negative 1 and 1. All right, that is to say, proper fractions, little fractions. All right, we don't care so much about big fractions. Now, a lot of times, parts of the Zone F will be excluded from consideration, right? A and B can't be 0 here. There'd be no point testing 0 for A and B because they told you that A and B can't be 0. But what about 1? Does 1 change anything? What about negatives? Could negatives have a role to play in showing that these two quantities don't have to be equal? Fractions? These are all like negatives and fractions, at least. No, 0 and 1 as well are things that behave weird with exponents, right? Take 1 to any exponent, it stays 1, for instance. And so testing these kinds of numbers could unlock something. It could shake something loose. And this is kind of a recognition of the fact that usually when we think about numbers, when we think about cases before testing them, and even sometimes when we go to actually test the cases, we get locked in this integer mindset above all else, and especially positive integer mindset, right? That everything's kind of a positive integer. Everything just behaves the way that numbers behave. We tend to think of numbers as like positive integers. We tend to think of how numbers interact, the way positive integers interact. But negatives do it different, right? Fractions do it different. And so these are going to be meaningfully different cases to test. And the more you use Zone F, the more you deliberately use it, the more you start tailoring your selections to the problems at hand. Like I said, in an exponents problem, yeah, 0, 1, negatives, fractions, all pretty relevant, right? But in, say, a fractions problem, 0 might be a no-go, right? Because of denominators and stuff like that. Extremes, really useful in an inequalities problem, not as useful elsewhere. That sort of thing. With all that said, then, what's the key here? Well, it turns out there are two ways you can get A and B to have different values, right? So let me just acknowledge up front that A and B could absolutely be the same if A equals 2 and B equals 2 and X equals 3. That checks out in the situation, right? 2 to the third does equal 2 to the third, so we've met the constraint. Nothing's equal to 0. Well, okay, then they're both equal. You got 2. You got 2. And indeed, in terms of answers available to you at that point, that would confirm that A and B are off the table. It's either going to keep being C or D is going to be the answer. Now, again, I would advocate against testing this case. I'm just doing it here to be complete, in case anybody was like, wait, how do we know? How do we know these things are equal? That's a good demonstration of it. But what kind of cases could make A and B unequal? One case. What if X equals 0 itself? Nothing said X couldn't be 0, right? A could be 2, B could be 3. And it checks out because 2 to the 0 is equal to 3 to the 0, in that anything to the 0 power equals positive 1. Well, in this case, quantity B comes out bigger. Usually if I'm testing cases like this, I'll kind of circle the middle if they come out equal, or box the middle, box the right if B comes out bigger, box the left if A comes out bigger. And if I see these boxes in two different places, there's one in the middle, there's one on the right, that's a pretty strong sign that the answer is D, and we don't need to do anything else in this problem. But again, cut down on that a little bit by having the conceptual insight up front. Yeah, A and B could be equal, and C is definitely a possibility, and B is the only other possibility, right? All right. Zona, really useful for testing cases, unlocks some of the less expected outcomes. Let's say in quantitative comparison, and the harder quantitative comparison gets, the more unexpected the outcomes are, right? Now let's see how quantitative comparison plays out in these different topics. One at a time, maybe two, depending. Starting with arithmetic. Arithmetic problems on the GRE just tend to give you a lot of numbers and ask about what you'd often consider kind of arithmetic things. That 1/5 to the -1, -2, -3 problem, total arithmetic problem up front. The 3 to the 7th minus 3 to the 9th problem, total arithmetic problem. And here's one more in a really common topic, percents. Right. I'll hang back for a minute, let y'all try it, and then we'll discuss. All right. Still waiting for our first successful answer. So what do we do here? We have an uncertain range for the price of an item, right? Which means D is on the table because there's something unknown, right? The price, while confined by these two bounds, is unknown. But it's still fairly arithmetic. The price is some number in that range, and then we've got these discounts that are being applied to prices, right? So we've got a couple of options here. We can try to do quantity A and quantity B a little bit algebraically, right? Get out there what it's going to be. Call the price P, right? Have this discount, have this $20, and maybe simplify some stuff. Or, because everything's numbers and these numbers aren't super bad, we can go to testing cases. And this would be a case in which you'd probably want to test extremes, right? Something close to the 90 side, the low bound, something close to the 150 side, the high bound. All right. You're going to do it algebraically first because, again, typically you'd want to, or at least I'd want you to, which, same thing, right? Price after a discount of 10% is that price minus 10% of the price. And then a subsequent discount of $20 brings you there. So 0.9 of the price minus $20. If, however, you're doing the $10 discount first, you've got this price minus 10, and the subsequent discount applies to this whole thing. So it'll be minus 20% of this price, which is to say we're going to have 80% of this price. Oops, minus 10. Or 0.8p minus 8. Now doing that gives us one big advantage. We can combine like terms. We can subtract the 0.8p over to the left to join the 0.9p. We can add the 20 over to the right to join the 8. We'll get 0.1p on the left after subtracting that 0.8p versus 12 on the right. Multiply both sides by 10. Who wants 0.1p? Now notice this comes out of nowhere. We're not canceling stuff when we multiply by 10, but we're still allowed to do it. It's a positive number. It's going to be fine. We get p. We get 120. And now we don't have to pick numbers anymore. We know that p is greater than 90 and less than 150. Its relationship to 120 then? Uncertain. And D is your answer. But look back on it after you do the problem that way. I'm looking back on it now. Would it have been faster to just pick numbers from the beginning? Could you have just done $90 or $100, which is on the 90 side real quick, and then switched it over to like 140, 150-ish dollars? Or would it have been faster to do this? Would you have gotten tripped up in the algebra? Looking at you, quantity B, this is kind of a weird way to start. Or would you have been totally fine? All right. That's going to depend a lot on your personal proclivities, right? But as a student of the GRE, honestly, you want to do the problem both ways. All right. And you want to reflect on it afterwards. Why was this way better here for me? Why would that way have been better in another problem? Things like that. Okay. The most depressing of answers. All right. Arithmetic. It looks like that. That is to say, even though that was an arithmetic problem, algebra can still really be useful, right? Numbers could have been useful as well. Logic will be useful in some arithmetic problems, especially those testing number properties, odds and evens, positives, negatives, and stuff like that, right? But let's talk Turkey. And by Turkey, I mean algebra, the thing we all give thanks for. Take a look at this problem. Y'all know the score. I hang back for a while. Shift my eyes around like somebody untrustworthy. You guys come up with an answer. I hope you're right. All right, so hopefully you've had time to work through it. Maybe you've got an answer. Maybe it's the right answer. I bet it is. You can absolutely start by testing cases. You've got some givens there that guide the cases you test. Y has to be positive. Y has to be greater than Z. No word on X, but I'm sure it's fine. But as you'll likely know now, you probably shouldn't. You've got 8 different variable terms in this problem between the two quantities. So every case you test, you're plugging into like 8 different things. You're choosing 3 different numbers. It can be hard to know which direction to go after choosing one number to the next number. And so algebra might be the way to go, especially because there are clearly like terms on both sides, both quantities, right? You have x's and y's and z's or z's on both sides. That then begs the question, what's the fastest algebraic approach? And this one may surprise you, all right? Because, of course, you can FOIL out quantity A and quantity B and get separate terms, and then you can cancel those terms, and you will eventually get to the right answer. But there's a move here, so powerful, so slick, that even if you tell your best friends you did it, they won't believe you. Y minus z is the same on both sides. Now, sadly, it's attached to x plus y or x minus y by multiplication, which means if we're going to cancel it on both sides, we'll need to divide. But that leads us to a perennial consideration when multiplying or dividing both sides of QC by something. Is it positive? Because if you know that y minus z is positive, you can totally pull this off. But if there's any doubt at all, if there's any uncertainty about whether y minus z is positive, you don't do it. It's bad. It'll get you the wrong thing. Luckily, this thing right here does ensure that y minus z is positive. You can algebraically move the z over to the other side. Y minus z is greater than 0. It's proved. And that cuts down on your potential work in this problem dramatically. So even when algebra is an option, there can sometimes be faster algebra and slower algebra, just like when testing cases is going to be the thing. There can be faster and more effective ways to do it and slower and less effective ways. That one move gets you rid of z forever. Never have to worry about z again. It's gone. It was a red herring. It was never really there. But it also puts you in a position to do one more great thing. Subtract x from both sides, because it's the same on both. It's the lead term. It's got no sign in front of it. You subtract x from both sides, it goes away. Then you've got y versus negative y. Now you can take this further algebraically. You can certainly combine those two y's into one term and so on. But at this point, it's probably easy to see that since y is positive, y is definitely going to be bigger than minus y. And a ends up being the answer here. All right. Don't test cases if you can combine like terms first. Yes, it is a fool's errand. You'll take far too long, and nobody's got the time on the GRE. That's how they designed it. All right. So often when you're getting an algebraic quantitative comparison setup, you actually do algebra. It's a bit on the nose, I know, but it works. All right. It works a treat. You should. And you're operating on that hidden inequality thing, which is to say, you're going to multiply or divide both sides by something. It must be positive. You only do that if it's positive. All right. If you don't know that y minus z is positive here, do the FOILing thing, subtract terms, etc. All right. Watch out for that. As long as you're cautious about that, there is no limit really to what you can do algebraically from there. Next topic. We're getting close, y'all. Geometry. So the thing about geometry in quantitative comparison is you can't necessarily trust the way the figure is drawn. Now, sometimes you can, right? But you never want to assume that a figure is drawn to scale. In fact, let's look at this one. Of all the options we could have chosen, this is the one we'll look at. That triangle looks fairly isosceles, right? A, C, and DE look to be parallel to each other in that figure. You don't want to trust that they are until you're told something about it, right? Until it's told to you or implied to you with like congruent angles or something like that, right? The figures that they give you in geometry QC problems are presumed to be not drawn to scale. The reason they give them to you is so you can get a sense of the general orientation of the shapes, right? Where they are with respect to each other. Like here, you know that triangle BDE is part of triangle ABC, right? You don't necessarily know until the words whether, again, DE is parallel or not, but you know it's part of that triangle. Furthermore, you know the relative positions of all those individual letters, where A is relative to D, where D is relative to B. Like D, E might actually be higher up in the triangle than it appears in this picture when we do all the math and everything, but we still know that D is somewhere on the left side between A and B. We still know that E is somewhere on the right side between B and C. Right? So they give you these figures to give you a sense of the orientation. So when they say things like DE is parallel to AC there in that given under the figure, you know which lines they're talking about. Okay. When they tell you that BE is equal to 2EC, you know they're talking about the top part of that right side being 2 times the bottom part of that right side, and so on. So don't take the figures as like sacrosanct, right? The way they're drawn may not be the way they actually play out, and you may not have enough information to know for sure. You can take them at best as like a possible case, all right? But they're really giving them to you so you can recreate them, so you know what the relationship is among all these letters, so you can label stuff and so on. All right. And particularly in geometry, it's true in geometry, it's true like across the board, but particularly it seems in geometry, every piece of information that's given to you is meant to be interpreted into something else, right? Just knowing that DE is parallel to AC is kind of like, well, I don't care. Frankly, I don't care. But knowing that this is happening in the context of a triangle and DE is inside that triangle and is parallel to one of the sides of the triangle, that actually means something. That means something for serious. It means that triangle DBE is similar to triangle ABC. And that means that the two triangles are going to be proportional to one another. They're going to have sides proportional to one another. They're going to have areas in some way proportional to one another, right? All we care about here is sides, though, because ultimately in quantity A, they're asking for a side, AC, that bottom side. We know that DE is 12. You'd want to draw it out on your scratch paper, so you could label that 12. And you know that BE is twice EC, but you don't know what they are, right? You could definitely model that as 2x and x. But if you've already done the work of noting this is similar triangles, and then the further interpretation of I expect this to be about ratios or proportions, then of course this piece of information hits a certain way. It means that that whole side is going to be 3 to like BE's 2 and EC's 1, right? That whole side will be 3x, BE will be the majority of it, it'll be 2/3 of it, EC will be the other 1/3 of it. Now, what does that mean for AC? Well, if the ratio of BE to BC is 2 to 3, that is, if one side of that top triangle has a 2 to 3 ratio to the full side of that, like, or the side of that full triangle, same side of that full triangle, we can apply that to the bottoms as well, right? DE is going to have the same ratio to AC because those are corresponding sides as well. And since DE is 12, do that math any way you choose, and AC is going to be equal to 18. So it's going to keep that 2 to 3 ratio. You can leave it as 12 over AC equals 2/3, algebra it up, and 18 is what it's going to be. And that means these two sides are so equal to each other. This is one in which D was on the table, by the way, because there's a lot we don't know about that triangle. But generally speaking, the more givens you're provided in a problem, the less likely D is to be the answer. We saw that a little bit in the previous problem where we had 2 givens, y is greater than z, y is greater than 0. And those 2 givens mattered in solving the problem and made it so that quantity A came out bigger. Similarly here, We've got the figure, we've got a parallel thing, we've got a proportion given to us, we've got an actual length given to us. That's a lot of information here for it to turn out to be D. I'm not saying D is impossible. I'm saying it's less likely the more information you have. Okay? Geometry QC can take all sorts of forms. Multiple figures are fairly common. And it's common to have to pick numbers or to benefit from picking numbers. All right. So in the last problem, no picking numbers. They'd given us a number. We kind of had to use it and the other relationships they'd proposed to us to get there. Right. But in this case, and in cases like it, where they just tell you, like the square has an area of x, or they just don't even give you that. They just say circle is inscribed in the square, full stop. It can be really beneficial to pick numbers. All right. That is to say, algebra is still going to avail you in geometry questions of all types, quantitative comparison and discrete quant. And if you're comfortable with algebra, algebra might well be the best way to go here. But there are going to be a lot of cases in which you pick numbers in geometry in quantitative comparison, and you only have to pick one number or one set of numbers or something like that, because the geometric relationships are usually so fixed to each other that whatever numbers you pick will just tell you the truth. You pick any number for x here, this whole thing is going to turn out the same way. And we're not going to proper do this problem, though. If you're watching it on YouTube afterwards, pause it, give it a try. It'll be fun-ish. And for anybody who just paused it and did it, good on you. What'd you pick? I'll never know. No use talking to your phone. But B should come out bigger. I'm almost sure. I'm almost sure. Leave it in the comments if I'm wrong about that, but I'm almost sure that B should come out bigger. Picking number can be different in geometry, quantitative comparison, than it is in all the other quantitative comparison types, because it's often not so much that you're testing cases as just kind of showing what the true relationships are with numbers instead of with letters. You can absolutely do this one with letters, right? Get the area of the square, subtract the area of the circle from it. You're given the area of the square, subtract the area of the circle from it. The radius of the circle will be related to the length of the side of a square, and so you can get the area of the circle in terms of x. Subtract it from x, see what you're left with. Pretty sure you're left with less than a fourth. I'd swear to it. And our last topic. We've seen a little bit of it before. Most data analysis questions are about averages, medians, could be ranges, but it could also get into probability, standard deviation, combinatorics. Right. That's our last problem. Take this one for a spin. I'll show you a couple more data analysis questions after this, but this is one to try. I'll hang back. You answer. Still no comments in the live session, and I'm shook. I'm shook. My favorite part of these sessions is when you guys are in cutthroat competition with each other. Alas. All right. The last problem we're properly going to talk about together, and that's because it's got one last point to make. Now, this is one of those cases in which quantity A is a hard thing to figure out, and quantity B is a normal number. So you'd look to quantity B and say, hey, is that number 25 significant in this problem? And the truth is, I couldn't really see how. I mean, it's kind of almost halfway between 18 and 30, but it's not really halfway between 18 and 30. And we're comparing it to the range, and there's no real reason to believe that 25 is a significant number range-wise. All right, so nothing immediately significant about 25 there that would make for just a quick logical win on this problem the way we had it with like 50,000 in an earlier data analysis problem. and the 50,000 meant something. So what do you do in these cases if that number is not significant? This is kind of the last stage of testing cases and builds on what we talked about in all the other situations. Optimization. One of the toughest topics in the GRE quant section is optimization, maximization, minimization. Some tests, they test it a lot. Some tests, you see maybe one. Just depends on luck of the draw. But optimization ends up being a big part of quantitative comparison because essentially if you're trying to prove D in an uncertain case like this, right? There's a lot we don't know here. These 4 ages, for instance. If you're trying to prove D, well, you're trying to produce 2 different outcomes. And one way to think about that when quantity B is fixed in place is, okay, what can I do to maximize the range that they're asking for in A? And what can I do to minimize that range? Right? And does one produce a certain outcome and the other produce a different outcome? Like, can I make A win and can I make A lose is really the question you want to go into this with, right? And this is definitely going to benefit from a bit of algebra. They say average, you can always use the average formula. The collective ages, the age of all the people collectively divided by 4, the number of people is 18, which means total age is 4 times 18 or 72. They have 72 years among them. Now, what's going to minimize the range here? Well, the only other requirement is that none of the other people be older than 30, right? And so what if we just make all of these ages 18, right? That'll totally work. Say they're all 18. In that case, the range of the 4 people's ages is 0, right? Range is the highest value in the set minus the lowest value in the set. But if every value in the set is the same, then that result is 0. 25 wins this round handily. And so your answers are, again, narrowed down at that point. Oops, not that way, mind you. That way. A and C are out. B just had a win. Maybe B keeps winning, but maybe you can get A to win and then you pick D, right? How can you get A to win? Now you got to think about maximizing the range. So what kind of things would maximize the range? Well, we made them all equal to 18 before, and we made them all equal to each other. So to maximize the range, we want to stretch out the highest value and the lowest value. The one rule we have to go off of is the highest possible value is 30, right? So let's say we make, yes, Abdul Rahman, GRE is the best test. You should take it. We got our first answer in on our last question. We've done it. I missed you guys. All right. Let's make person 130, right? The highest that any of these ages can be. What does that leave us with? That leaves us with another 42 years to play with, right? That's 30 of our total of 72 years. But now we got to focus on making one of these people the lowest they can be. And really the question is, can we make this range bigger than 25 or even equal to 25, right? So could we make person 2 have like be a 1-year-old, right? Or a 5-year-old or a 4-year-old, or any of those will create a different relationship. Could we do it? Well, that right there is 31 years accounted for. We have 72 years to account for overall, which means the other 2 people would have to be collectively 42 years old. That's totally possible. You can do that any number of ways, 21 and 21. We'll do it. And in this case, now the range of the 4 ages is 29. And quantity B loses. And in, frankly, kind of an embarrassing way. Don't know how you're going to recover from that. Quantity B, D is the answer. As 9002 says, yeah, D is absolutely the right answer here. All right. But if quantity B had been like 31 or something, I mean, maybe that would have been, again, a bit on the nose, but it would win, right? So you kind of do have to do this max-min game, even if it seems pretty clear up front that there's going to be some range to it. If the average had been smaller, right? If the average age of these people had been like 44 years old or something like that, there again, you might have a little bit of trouble, or like honestly more like 34, let's say 33, who knows what, 30. Depending on conditions, it can go a different way, right? Max-min thinking, optimization thinking is kind of the last frontier of testing cases. You want to be thinking about zone F when you test cases. You want to go into testing cases having had some conceptual or algebraic insight whenever possible. But if it's truly a kind of testing cases problem, maxing and minning is kind of big. It's kind of what we saw with the $90 to $150 price of an item in an earlier question, where if you tested the extremes, the min and the max, you'd get different results. And you would have shown that that was D as well. All right. But we had an algebra approach. All right. Other examples of data analysis questions. Again, things asking about averages and medians, but also things like this, asking about combinatorics. If you're playing from home, pause it, try this one, see what you come up with. Leave your answer in the comments. And I'm sure a consensus will develop. And that's it. That's all the question types. All right. And the thing I really want you to take away from this is all approaches can work in every topic. Like what topic you're dealing with here doesn't have much to do with how you can approach the problem, right? How you can approach the problem is more about the looks in the quantities. Do you have a hard thing to solve in A and a plain old number in B? You might approach it logically, right? Do you have like terms in quantity A and quantity B? You might approach it algebraically. You probably should. Give algebra and logic, write a first refusal, go to numbers after that. Once you've cleared away some of the noise, had some kind of insight, or exhausted those options, come up with nothing, and just want to get something right. Remember that a lot of these questions are going to show up trying to get you to pick a certain answer, and your job is to fight against that, right? Because if the GRE is ever trying to railroad you towards something in quantitative comparison, there's a really good chance it's a trap, right? And so push back against that. Be organized in how you test cases. Use zone F to think about uncomfortable cases that might actually produce different outcomes, and study optimization, because even if you don't get any proper optimization questions on the test, and you usually will, a lot of quantitative comparison questions benefit from optimization style thinking. How can I minimize this quantity? Cool. Now how can I maximize this quantity? All right. And I leave you with one last super challenge problem. If you're watching this on YouTube or even watching this now, screenshot it, try it, and leave your answer to this one in the comments as well. But with that, yes, I bid you the warmest farewell. Come back next week for GRE Prep Club's last episode in this series. And if you haven't seen the other ones, if you, like Abdul Rahman, are totally new to the GRE facts, check out all the other videos in this playlist. It's a pretty good playlist. Obviously not the ones I'm in, but Logan and Chris, my esteemed colleagues, they really know their business. So check out those videos, all right? And if you have anything else that you need test prep wise, check out GRE Prep Club, check out Manhattan Prep. You can sign up for free resources and free trial class even there. With that, I will leave you. Have an excellent rest of your day/night/life. And I'll see you around. Best of luck to all of you.